All right, I better get going. We got a lot to do. Good morning, everybody. Welcome to exciting but cloudy morning, Chem 1105, with your host, me, Dr. White. Hope you all had a great weekend. Saturday morning, I did battle with Mother Nature, mowed the lawn, trimmed some bushes and stuff like that. The weather was beautiful. When I in the summer, I usually get going about 7:30. By 9:30, quarter to 10, I was done sitting out on my deck enjoying the beautiful weather. Oh, it was beautiful Saturday morning out. And if you felt the wind on your face like I did, I was probably the only one in my neighborhood who was thinking, those are molecules of oxygen, nitrogen hitting me in the face. That's what wind is. All right, before I get started, I want to do a serious public service announcement. If you've been following the news, the Delta variant of the coronavirus is pretty serious and starting to spread throughout the United States. But if you're vaccinated, you've got a 90% chance that it won't even touch you. So if you haven't been vaccinated, please get vaccinated. Also, wear a mask too. I still do when I go out just to be safe, even though I've been got both my shots, the Pfizer vaccine, beginning of April. So it took me a while to get it in to get an appointment, then all of a sudden opened up. Now you should have no trouble. Get vaccinated. I have a history of having bad reactions to any kind of shots. One time when I had a tetanus shot, my whole left arm was paralyzed for 3 days. Just didn't want to do anything. Well, when I took the Pfizer, yeah, you had a little discomfort in your muscles in your arm for a couple of hours, but it wasn't bad. And I was shocked that it didn't do anything bad to me, which I was grateful. And now I'm protected. Get vaccinated. All right, for those who are wondering, here's my, I don't know if you can see it, my notes for today's lectures. All right, as I sent out, I'm doing updates. I sent out an update email. You should be reading your email on a daily basis. Lab number one is due tomorrow. Make sure you upload it to the assignment area Blackboard. It's 10 points, 10 easy points. It's not a hard lab to do. And if you don't, you get 0 points, which is not going to be good for your grade in the long run. So you have a small window tomorrow and up till Tuesday or Wednesday morning or Tuesday afternoon. I forgot which one I set to get it uploaded as a single PDF file in the assignment area for that lab. Are files that will teach you, if you don't have a scanner, how to make a PDF file with your cell phone. All right. Drew, I look on assignment area. I think it tells you the deadline is due 5 p.m. Thank you. That gives you plenty of time. You've had since last Thursday to do it. So keep up with the labs, especially in the summer. Uh, since we're not face to face, when we're in a lab, I can pester people. Where's your lab? And but anyways, keep your and Disha, thank you. All right, another thing on Tuesday in lab, I'll be doing two things important. One, besides lecturing them first, or not lecturing, one, I will go over how to use a scientific calculator using scientific notation, which you will need to know for our test and the final. Also, on Tuesday, tomorrow, I will go through Chapter 1 and Appendix A2 and A4 problem set. Make sure you try them before I do. Will I go through the whole thing? No, but I'll go through some I think you should know. Also, I entertain questions. If you have problems on the problem set, tomorrow, ask questions. Remember, in my class, in my world, There's no such thing as a dumb question. All right, I looked at the schedule of what we're doing tomorrow, and it's too busy. So instead of tomorrow, on Thursday after lab, those who want to stick around, I will teach you my method, how to reduce anxiety. And it works like that. Students have gone from getting D's, F's, even maybe low C's, to high B's and A's on my test. And also you can use it in other classes too. I will cut that out of the video, but if you can't make it today, those who couldn't, I will teach it to you during my office hours. Speaking about office hours, I set them because last semester it worked well. Doesn't mean it works well with every class. If you think of a better time Monday through Thursday, before 9 and after 4, because from 9 to 4 I'm teaching all 4 days, let me know and I can change my office hours. So if you think of a better time besides Monday and Wednesday from 6 to 7:15, let me know. All right, I think we're caught up with all announcements. Let's get to work. Now, last week, we started talking about a couple of things. One was molecular formulas of molecules. And one of the things, and by the way, if you could turn your webcam on, it makes Dr. White happy. And one of the things I asked you was, in this compound, how many atoms are there? And this is 1 calcium and chlorine, and there are 2 of them, plus 2 equals 3. Next, I showed you if there's a bracket like this, whatever you see inside the bracket is multiplied times the number subscript to the right of the bracket. So this is 1 calcium, 1 oxygen, but times 2 is 2 oxygen, 1 hydrogen, but times 2 is 2. So there are 5 atoms in calcium hydroxide. Now, let's you have a try. How many atoms are in this molecule? Your turn. All right, one thing I will ask in Zoom, can you please put either your first or last proper name that's on the official list that you registered for on your Zoom? I'd appreciate that. That way I can take attendance and know you're here. All right, let's do this. How many atoms are in here? Na, sodium, 2, 1 sulfur. Ooh, oxygen, how many? 4. And if I add this up correctly, that's 7. Remember, I write my 7 that way. Oh, let's do one more. These are fun. This is called ferric nitrate. And how many, by the way, both numbers are 3. How many atoms are in ferric nitrate? Oh, I should have mentioned Na2SO4, sodium sulfate. This is the molecule you see in those little packages, like when you get electronics or optical equipment, like binoculars or other things, where it says, do not eat this little package. And what it does is that absorbs moisture, and that's why it's put in there to keep it dry. All right, thumbs up, people. If you're done, give me a thumbs up with your emoji on Zoom.
Hey, I have a question.
I do.
Is my name not popping up?
What's your name? So I don't know.
Oh, I'm sorry. It's Jada, but I had to get a new computer because I couldn't download the lab. I had to get a new computer. So if it doesn't show my name, I just got to figure out how to change it.
All right. If not, just send me via direct chat message your name, and I'll know you're here.
Okay.
Dr. White's
Okay.
Zoom expert, sort of. All right. All questions are good questions. And let's go. How many atoms are in this molecule? Well, there's one iron. Ooh, brackets. Remember, you multiply whatever in the bracket times the number outside. One nitrogen times 3 plus 3. Ooh, look. 3 oxygen times 3. 3 times 3, I hope, is 9. So if I add this correctly, 1 plus 3 plus 9, that's 13. So that's how many atoms there are. And I like to start out with a little review because practice makes perfect, which helps you get a good grade on the test, which helps you get a good grade in my course, which will make you happy and makes me happy. All right, let's move on. It's time to find where did I hide it. There it is. I'm going to move this up here. All right. Thumbs up, people. Do you see the periodic table on your screen? Thank you. All right. This is the periodic table. Ooh, time for commercial from Dr. White. Remember, learn your chemical symbols and their names for tests 1, 2, 3, and 4. You're not going to learn chemistry the day before a test. And I showed you this last week. The first column, and I'm going to sneeze. I think I'm allergic to the periodic table. Oh no. Anyways, the first column, not counting hydrogen, all right, there's the X. The first column, there. The first column, not counting hydrogen, lithium, sodium, potassium, and others, but those are the only 3, are called the alkali metals. And you should know what are the alkali metals on a periodic table. You should be able to find one and give an example with its chemical symbol and name, like Li is lithium, Ni sodium, K potassium. Next to it are the alkaline earth metals. And the only ones I asked you to learn the chemical symbols for were Mg magnesium and Ca calcium. Now, if we go all the way over here, and this periodic table doesn't have it set up, but right here, fluorine, chlorine, bromate, and iodine, there are others, but I've never used them and you won't. So those are the important ones. Those are the halogen in the periodic table. These elements are called the halogens. Ooh, that reminds me. How many of you have ever seen or heard about halogen lights? They make them for many things. If you go in Chicago, those real bright street lights are halogen lights. And halogen lights are called that because the gas inside that they put electricity to make light are the halogens, fluorine, chlorine, bromine, or iodine. How about that? It's in your everyday life. And finally, the last column is the noble gases. It used to be called the inert gases until some very sharp chemists found a way to make them react, and so you couldn't call them inert anymore. And they were given the name about 15 years ago, maybe 20, which is not that long ago. They were renamed noble gases. And you should know on a periodic table what are the noble gases and be able to give an example of one, both its name and its chemical symbol. AR, argon. Dr. White used a lot of argon when I was working in grad school. And I've never worked with it, but I do know krypton, KR, is a colorless gas, not a green solid, that will kill Superman. Now, on our test, you will not be allowed to go on the internet. And I'll have a way of determining that. And what should you be doing? Give me a second while I open something up. All right, thumbs up, people. Does everybody see the periodic table on their screen? Thank you. All right, this is the periodic table you will be using. In fact, either today or tomorrow, I'll email out a copy. When you take a test, this will be one of the files you can download. And if you don't have a printer, you can look at it on your monitor. I'll trust you there. And notice there are no names on there. That's so you learn them. And here, the first column, not counting hydrogen, are the alkali metals. Second column are the alkaline earth metals, magnesium and calcium. Over here, second to the right, with the number 7 over it, are the halogens, fluorine, chlorine, bromine, and iodine. And finally, the last column with the number 8 over it, you'll learn what those numbers are in a couple of days, are the noble gases, helium, neon, argon, krypton, xenon. And you should know those. Now, the rest of these, like stuff down here, like californium. Where's californium? Somewhere down here. I've never used 102 lawrencium. You're never going to use, I'm never going to use. So that's why I'm not asking you to learn that. But other ones like copper you use, silver you could use, gold, a lot of you've used. They have rings or necklaces or other things made of gold. And those are important. Same thing with palladium and platinum. Those are used in the catalytic converter of your car or your friend's car or your parents' car. So those are things you should know. All right, guess what time it is? I love that. It's new chapter time. We're done with chapter 2 and we're going to chapter 3. So I better open it up. And why am I so happy? We get to talk about some real chemistry now. And chapter 3 deals with the atom. And the switch is on. You should know. Oh, let me be subtle today. It's Monday. And the atom. The atom is the smallest particle of an element that retains the characteristics of that element. That's an atom. And you should know, if I ask on a test, 3 points, what's an atom? That's the smallest particle of an element that retains the characteristics of that element. example would be gold is shiny and yellow. Sodium, unlike gold, you put it in water and it reacts quite violently. Gold, if you put it in water, doesn't react at all. And silver atoms, silver in general, will react with oxygen to form silver oxide and tarnish. So the atom, the smallest particle of an element that retains the characteristics of that element. Now, I'm going to turn the switch off, click, but this is something I do want to cover. And that's dealing with Dalton's atomic theory a long time ago, but in this history of mankind, not that long, but in the early 1800s, a great chemist or scientist, I don't know if they call them chemists back then, Dalton. And Dalton, and let's take a look at this. And does everybody see the picture, thumbs up people, of John Dalton on the screen right now? Thank you. And Dalton was a great English chemist. I guess they noticed he did physics and meteorologist too. And he's best known for the atomic theory. And in England, there's a major chemical society called the Dalton Society. Now, what is his theory? At the time, this was revolutionary, and a lot of people didn't believe this theory, but eventually it did become catch on and has now been proven. And first of all, every element is made up of tiny particles called atoms. Dalton was the one who came up with the word atoms. Now, if you read, and I'll be honest, I don't speak Greek, but Dalton picked the word atom from, I think the Greek word is atomos or something similar. That means you can't divide it into anything smaller. And an atom, by physical or chemical means, listen carefully, by physical or chemical means, cannot be divided into smaller particles. So that's an atom. That was his idea. He also came up with the idea atoms of a given element are identical to one another and different from other elements. So if you have atoms of sodium and atoms of, say, copper, they're different. But if you're in Chicagoland, if you're in, I don't know, where's another, Spokane, Washington, one of the few cities in the United States I haven't been to, but guess what? Sodium atoms are going to be sodium atoms. Copper atoms are going to be copper atoms. And this was quite revolutionary. Again, switches off, but this is still background I'd like you to know. Now, continuing on with his great theory, atoms of two or more different elements combine to form compounds. A particular compound is always made up of the same kind of atoms and the same number of atoms. And what does that mean? Water is H2O. And if you drink water here in Chicagoland, that water is H2O. If you find water, say in the rings of Saturn, it's going to be H2O. If you find water on Mars, it's H2O. Or if you go anywhere on this planet, water is H2O. And that was his idea. And next, he came up with the concept a chemical reaction involves the arrangement, separation, or combination of atoms. Atoms are Oh, excuse me, I'm getting all choked up over this. So excited. Oh, that was lame. But anyways, atoms are never created or destroyed during a chemical reaction. So when we have a chemical reaction, all you do is rearrange, change where the atoms are, but you never create or destroy atoms during a chemical reaction. All right, now switches on. Quick, you should know this. Parts of an atom. The parts of an atom are called subatomic particles. Those are very, I'll never ask on a test what's a subatomic particle, but you should understand at least the definition. Very small particles that are the building blocks from which all atoms are made. How many of you know what a submarine is? That's a boat that goes under marine water. Good news, I'm not going to sing Yellow Submarine. You know, we all, no, I said I wouldn't sing it. It's one of my favorite Beatles songs. That and a few others. But subatomic particles are the particles that are smaller than the atom. What are they? And the subatomic particles, hold on, I have to be subtle. See how subtle I can be? All right, the first subatomic particle are the electrons. Electrons are subatomic particles that have a negative charge. Electrons, negative charge. You should know that. The next one are the protons. And the protons are subatomic particles, particles that make up an atom of all elements. And those are protons. And the protons possess a positive charge. So electrons, negative charge subatomic particles, protons, positive charge, and the final one are the neutrons. And the neutrons have no charge. So if we're in class right now, I'd be saying, you don't have to turn on your mic, but everybody all together out loud, if you're not in the library, say it out loud. What's the first subatomic particle? It's the electrons. What's the second subatomic particle? The protons. What's the third one? The neutrons. Oh, that was pretty quiet. Let's do it again. Come on, what feeling? What's the first subatomic particle? The electrons. What's the second one? I'm listening. Yep, the protons. And the third one are the neutrons. And those are the subatomic particles. You should know electrons have a negative charge, protons have a positive charge, and neutrons have no charge. How many of you have heard of the TV program? I haven't seen it in a while. I haven't looked for it either. Jimmy Neutron. Have you ever heard of that TV program, Jimmy Neutron? If they had asked me, I would have called it Jimmy Electron, because the electrons are far more interesting. Uh-oh, I think I just did a generation gap on you people. Jimmy Neutron isn't that old. Oh, wow. But anyways, remember the three subatomic particles: electron, proton, neutron. Electron has a negative charge, proton has a positive charge, and neutron has no charge. And you should know that. Hint. Now, the question is, how did I figure this out? Well, chemists did experiments. One important experiments I like to talk about is Rutherford's gold foil experiment. Now, what was Rutherford's gold foil experiment? And let's go out to the internet. All right, thumbs up, people. Do you see on the upper right a red box with something red in it shooting toward? Thank you. All right, this is a gold foil experiment. What he had was a source of very energetic big particles called alpha particles. And he had very thin gold foil. And around it, there was a detector. And this detector would fluoresce, in other words, show a bright spot wherever those alpha particles were. And think of it this way. It's like shooting cannonballs at tissue paper or Kleenex. I'm using a generic name for Kleenex, or for those who don't like Kleenex puffs, you shoot a cannonball at it, it should shoot right through. Well, Rutherford had this experiment done, and lo and behold, the particles scattered. Most of them went through, but a lot of them scattered to the side, and some even came back. Now, uh, it's time for me to teach you about research and academic research. If you've been a PhD student, you work for a professor, someone who has a PhD. In my case, I was so lucky to work at Michigan State with my advisor and his research group, Dr. William Roosh. And Dr. Roosh taught me, laid the foundations in me how to be a great, hopefully I'm a great or very good synthetic organic chemist. Now, the way it works is you join a research group, and then you join that group because they're doing research in areas you're interested. I did. And you're given research project to work on. Now, the way it works is you get results, you show your professor, and if it's something unexpected, I know Dr. Roosh did to me and other grad students in our group, he'd say, go back and do it again. That doesn't look good. That doesn't look right. And if you did it again or two more times, you got the same results, and it's unexpected. He didn't have a beard, I do. But anyways, back then my beard was out to here because I didn't have to worry about wearing gas masks like I do now. If I go to a chemical plant for consulting, but anyways, he'd come out and say, show me, I want to watch you do it. And I can envision Rutherford having a graduate student do the experiment, and the graduate student came in, some of the particles bounced back. And Rutherford said, what? No, go do it again. And he came back, same result, do it again. Same results. And he probably went out and said, show me. And this was amazing. Think of it like shooting a cannonball through tissue paper, and some of it bounces back. And what it helped Rutherford do, and you should know, is determine the nature of the nucleus. And what is the nucleus? The nucleus is the center of an atom. And you should know, first of all, the nucleus is the center of an atom. And you should know Rutherford's gold foil experiments clarified, that means figured out important things about the nucleus. One, the nucleus was very dense. And this very dense center is why those high particles, some of them hit it and bounce back. And you should know the nucleus only contains protons and neutrons. Again, Rutherford's gold foil experiment helped clarify or learn about the nucleus of the atom. And the nucleus of the atom is the center of an atom. And you should know that. And you should also know that the nucleus only contains protons and neutrons. And it's very, very dense, meaning heavy, solid. That's why it bounced back those heavy particles. So that was Rutherford's gold foil experiment. This was about 1900, not that long ago in the history of mankind. Now, switch is still on. When we talk about atoms of elements, they have two things, an atomic number and a mass number. Now, the atomic number, by definition, equals the number of protons in the nucleus. Something I'll go over more in the coming days. All atoms have a net zero charge, which you should know. Therefore, if the atomic number equals the number of protons, remember protons have a plus charge, and all molecules have a net zero charge, the atomic number also teaches us the number of electrons. So the atomic number, that's the number of protons in the nucleus of an atom for a specific element, equals the number of protons. But because all atoms have a net zero charge, it also equals the number of electrons. So the atomic number, which I'll show you in a little while, can be found on the periodic table, equals the number of protons, equals the number of electrons. I see a question or a comment. One of your colleagues just asked, is the practice problems the same questions on the test? And the answer is no. Are they similar to the questions on the test? Yes, they're why I call them practice problems. They won't be identical, but they'll help you practice for stuff on the test. And if we're in a classroom, I'd be doing this on the whiteboard, and you just have to be patient and wait. So the question is, how many protons and electrons are in hydrogen? Well, you have to go to your periodic table. Everybody see the periodic table? Thumbs up, people. Thank you. And hydrogen, you need to know the chemical symbol for hydrogen. Let me make this a little larger. And hydrogen, chemical symbol is H, and the number in the upper right-hand corner is the atomic number. The atomic number for hydrogen is 1. Atomic number tells you how many protons and neutrons hydrogen has, and that is 1. So the answer here would be 1. Now, carbon, you have to know the chemical symbol is C. And if we look at the periodic table, where's carbon? Right over here. And if you look in the upper right-hand corner of our periodic table that you will use for test number 1, 2, 3, 4, and the final, you'll see the number 6. That's the atomic number. And the atomic number tells you how many protons, in this case 6, how many electrons, 6. And let's do one more because these are fun. Wait, I think I saw something. Somebody beat me to it. All right. The next one was bromate. Where's bromate? And you have to know not only this chemical symbol, but where to find it on the periodic table. And bromine Br is right here. And the chemical symbol Br, bromate, what's the atomic number? The number in the upper right-hand corner, 35. And the atomic number tells you the number of protons and electrons. And therefore, I could put in 35, 35. And you know I'm going to share the fun, so let me give you one to try. And that would be sodium. And I'm going to switch right back. How many protons, how many electrons are in sodium? Your turn. See how nice I am? You have fun too. And when you're done, thumbs up, people. Give me a thumbs up or any other emoji you'd like to use on in Zoom. All right, I think we're all done. Let's take a look at the periodic table. And the question is, how many electrons and protons, or protons and electrons, does sodium have? You need to know the chemical symbol sodium, Na. How many electrons and protons? 11. And therefore, sodium has atomic number 11 and it has 11 electrons, 11 protons. And you have to know the right chemical symbol. And that's why I've been saying, learn your chemical symbols. Remember sodium, Na. You don't have to write this down, but here, 11 and 11. Oh, let's have one more. Oh, what would be a good one? Important molecule in our daily life is nitrogen, or atom, I should say. And how many protons and how many electrons does nitrogen have? And let me open up the periodic table again. And there you go. How many electrons and protons does nitrogen have? All right, anybody need more time? Or I should say, give me a thumbs up when you're done. Uh-oh, it's don't do thumbs up day. All right, let's do it. Everybody, do you see on your screen the periodic table? Nitrogen, chemical symbol is N. In the upper right-hand corner, not below, above, you'll see the number 7. That's the atomic number for nitrogen. Nitrogen has 7, atomic number of 7. And remember, the atomic number tells you the number of protons and electrons, and therefore nitrogen has 7 electrons, 7 protons. And this is a skill you should have. As I've been saying, you should know the chemical symbols and their names for only the ones I asked, not the whole periodic table, because most of those you're never going to use. I've never used them. I've been doing chemistry a few more months than you have, few more months. If I look at the clock, it's just about time to take a break. So let's take a break, come back at 9:55 in about 5 minutes. I'm going to get up and stretch. I'll see you in 5. time to get started again. All right, remember we were talking about the atom. The atom is the smallest particle of an element that retains all the physical and chemical properties of that element. An atom cannot be by physical or chemical means broken down into anything smaller. And just to remind you, atom is made up of subatomic particles, and those particles are the electrons, protons, and neutrons. The electron has a negative charge, proton plus charge, neutron no charge. And in the nucleus, which is the center of an atom, that only contains protons and neutrons. And how do we know how many protons are in an atom of an element? The atomic number. And the atomic number equals the number of protons. Since all atoms have a net zero charge, it also equals the number of electrons. And before our break, we went through how to find that. Now, there's something which we'll deal with later called the atomic mass number of an atom. And it turns out by definition, and this I'm turning the switch off, click, this won't be on a test, is the sum of the number of protons and neutrons in the nucleus. Sometimes the atomic mass number is called the atomic weight. And if we look at the periodic table, for now, I'm just going to briefly mention it. The number underneath the chemical symbol is the atomic weight or mass. I use them interchangeably. A lot of chemists would be screaming, you can't. Well, we're not leaving this planet. At least you all agreed, at least through the summer, so I can do that. And if we look at sodium, the atomic number is 11, but the molecular atomic weight is 22.989. If we look at oxygen over here, O, atomic number is 8 electrons, 8 protons, but the atomic mass is 15.999. And we'll deal with that later in the semester. I just wanted to point this out. Now, there's something called isotopes. And isotopes are atoms that have the same, of the same element, have the same number of electrons and protons, but different number of neutrons. Again, switches off, click, but I just want you to know about it because isotopes play an important role in our everyday life. And the atoms are made up of each element of different amounts of isotopes. The electrons and protons are the same, but the number of neutrons are different. And for certain atoms, there's one isotope that's the dominant one or in the greatest amount. Example, carbon, the isotope of carbon is 12. That's the one greatest, but there are other isotopes. How many of you have ever heard of carbon dating, where archaeologists can take some carbon and I've never done it, but determine the date of something, how old it is. And they do that by measuring the different isotopes. And isotopes, which we won't really go into, the larger ones decay, lose some neutrons to go to smaller ones. And I think the decay rate for carbon 14, let's look up something real quick. And I was right. Why do I remember these numbers? Carbon 14 takes 5,730 years for it to decay, half of it. And I'll teach you later on the semester what does half-life mean, to go to carbon-12. So if you measure the amount of carbon-14, and since this planet started, the amount of carbon-12 and 14 has remained relatively constant, you can determine how old something is. That's my knowledge of carbon dating, because it's an area I've never worked in, but that deals with isotopes. And remember, isotopes are of the elements have the same number of electrons and protons, but different neutrons. So they weigh differently because the weight mass of an element is the sum of the protons and neutrons. Now, switch is totally off. If you read in your book, they have a thing for nuclear symbol. I have never used my whole career, so I just thought I'd point it out for you. Put the symbol, the atomic mass number, and Z is the atomic number. So that's just for different isotopes. All right, now, switch is off, but this is something you should know about. Atomic weight or atomic mass is the weighted average mass of all naturally occurring isotopes of the element based on the abundance, how much, and the mass of each isotope. So for magnesium, if you look in your book on page 112, they show you the calculation. And if we look at carbon, notice on the periodic table, the atomic weight is 12.011. And the most abundant isotope of carbon, carbon-12, has a atomic mass of 12. That's like, I don't know, 90% or higher. And you multiply that number by the amount of carbon-13 and carbon-14, and you add them up and average them, add those weighted average percentage times the atomic mass of the isotope, add them up, and that's how we get the atomic mass right here of carbon. Same thing for nitrogen, oxygen, and all the others. Now, some instructors at this point expect you to know how to calculate atomic weight by knowing the abundance of isotopes. I've been in chemistry a lot longer. No, I better show it to you. Everybody see my ring? Can you see the date on there? 1972, right there. That's when I got my bachelor's degree in chemistry. I've been doing chemistry a few more years than you have, a lot more years. I have never, ever, ever had to calculate the atomic mass by the isotope abundance. You go to the periodic table. So good news, Dr. White lives and has worked and still does work in the real world. I do consulting besides teaching. And since I've never done it, why should you? So you won't. You can say, thank you, Dr. White. You're welcome. Modest, aren't I? Now, let's have some fun with the periodic table. We've done this, but let's do this again. I see a question. You're welcome. All right, let's locate some elements. Let's determine the atomic number, the number of electrons and protons, and the atomic mass of the element. So I better get my whiteboard up. For what's the atomic number? First of all, find out number of, oops, I promised I wouldn't write. This right here is shorthand, the ampersand for number. And I'll use that throughout. All right, let's do a couple. I'm going to let you do it and then I'll do it. For calcium, find the atomic number, atomic mass, and the number of electrons and protons. And let me show you your periodic table. Go. Let me make this a little bigger. I see people are already doing that. I'll give you another 7.6 seconds. 7.2, 7.4. I got a slow watch. 7.6. Time's up. Calcium. What's its chemical symbol? Ca, right here. Excuse me. And what's the atomic number? 20. What's its atomic mass? 40.078 on this periodic table. And how many electrons and protons? 20 electrons, 20 protons. All right, let's do the same thing for iron. What is the atomic number for iron? What is the atomic mass for iron? And how many electrons and protons does iron have? Go. I like that, go. All right, time's up. Let's take a look at what did I ask for? Iron. What's the chemical symbol for iron? Fe. It's right here in the periodic table. And what's the atomic number? Upper right-hand corner, 26. What's its atomic mass? Below the element symbol, 55.845. How many electrons and protons? 26, because the atomic number equals the number of protons and number of electrons. Let's do one more, and that's what's the atomic number, what's the atomic mass, and how many electrons and protons does mercury have? And mercury at room temperature is a shiny liquid. They used to be in thermometers until they found out how deadly they were, and now you use electronic thermometers. Again, you're looking for the atomic number, atomic mass, and the number of protons and electrons in mercury, which is also the name of the first planet from the sun. All right, let's do it. What's the chemical symbol for mercury? Hg. It's right here. What's its atomic number? 80, number in the upper right-hand corner. What's its atomic mass? 200.59. How many electrons and protons does mercury have? 80. It has 80 electrons and 80 protons. And that's how you use the periodic table. Do we have time? Oh, we do. Let me see if I can find it. Give me a second or two or three. All right, thumbs up, people. Do you see right here in the upper right? Looks like a maze with a little silver drop right here. Do you see that? All right, when I was a kid, it wasn't as complex as this one. You had this toy, and this toy had a drop of mercury, and it had a cardboard back and a plastic front, and a little maze in here, and you could maneuver the drop through that. This was back in the 1950s when I was a kid, very young, and my friends had it, I had it, and today you're not going to buy one. Oh, I don't know about that. I thought they were all gone because mercury is a very dangerous substance. Mercury, when you get it in your system, is a cumulative poison. You never get it out of your body. And guess what? It'll eventually do serious harm to you or kill you. And it still blows my mind that back when I was a kid, we had these little toys with mercury in it and cardboard. I wonder how many children ripped that and where'd the mercury go? Well, it's hard to clean up too. Mercury spills are very hard because it's a real weird solid that doesn't absorb into paper or sponges. What you have to use is steel wool, and you can pick it up that way. But that was a mercury toy. Let me see something about. And a form of mercury poisoning that happened long ago in Japan back in 1956 in a town called Minamata. And it caused horrific problems, health problems to the inhabitants there. And it was one of those sad occurrences in chemistry where people didn't realize until later on how dangerous mercury and mercury compounds are. And by working with it and getting it into the life like seafood and etc. and from wastewater that was dumped into the sea caused serious problems. Sad, sad, very sad. All right, let's continue on. So we've done our practice time with the periodic table. I'd highly recommend you do your own with chapter 3 practice problems. Now, from Rutherford's experiments, the electrons and the protons and neutrons are in the center of a nucleus, which is round. Now, if the protons and neutrons are in the center of an atom, the nucleus, where are the electrons? Good question, thank you. The electrons are all around the nucleus, what we call the electron cloud. But in order to understand that, I have to teach you some stuff about electromagnetic radiation. Now, switch is totally off for these slides, but there's still important background information you should know. And let's talk about electromagnetic radiation. This is energy that travels through space. What's an example of that? All right, everybody see on their screen right now? Let me check. The this little squiggly red line, this is the electromagnetic radiation. And there are different types of radiation. Radio waves are, microwaves, then we have infrared light, visible light, the white light you're seeing, then ultraviolet light, then X-rays, then gamma rays. As we go from left to right, the electromagnetic radiation is more energetic. So electromagnetic radiation is energy that goes through the air, space. And well, I guess you don't need air because sunlight is electromagnetic radiation and it goes through outer space and there's no air in outer space. Now, when we talk about electromagnetic radiation, again, click to switch us off. Electromagnetic radiation is like waves. And just like ocean waves, electromagnetic radiation has both wavelength, what's the distance between it, and how often they move, frequency. It's like if you turn a radio to a certain station, you know what's the frequency of it, and that's because the electromagnetic radiation of the radio, like FM and AM radio. Now, we have what's called the electromagnetic spectrum. Switches off, but you'll see how this all teaches us important things about electrons, which are the subatomic particles that make up the atom. Very important part, at least in my opinion, personally. And those are the arrangement of all the various forms of electromagnetic energy in order of decreasing energy. And if we look at the example I have right now, here's the electromagnetic spectrum, and it goes from small, and you see it down here also, low energy to high energy. And if we look here, right in the middle, we have the visible spectra, Roy G. Biv. Ooh, that reminds me. How many of you remember Roy G. Biv from high school? When you were in high school, chemistry or science, maybe even earlier, you had to learn what were the colors of the spectrum. White light, like is around me, not that I own it, white light, but the other type of white light. Oh, that was an awful joke. But anyways, is made up of different colored lights, and they all blend together to give us white light. But you can separate it with a prism. Nope, I don't have them up here, they're downstairs. Dr. White has a collection of a couple of really big prisms. They're cool. And a long time ago, I decided I want some, and I went out and got them. Anyways, when you put light through a prism, it separates into the spectrum, the rainbow of colors that make up white light, and that's Roy G. Biv. And Roy G. Biv is the way you remember red, green, and so on, blue. Let's see if I can find one. And does everybody see in the upper right-hand corner, this prism? No, it's not a Pink Floyd t-shirt, even though they've used that. And white light comes in and is separated into different colors, red, yellow, green, Roy G. you can't see the orange, but it's red, orange, yellow, etc. That's where Roy G. Biv. This is a nicer one. It shows it better. And that's because of the different wavelengths of white light. White light is a combination. Now, you might wonder, what does this all mean? Why am I learning this? Which is a good question. Let's talk about atomic spectra and energy. Again, switches off, but this is important background information. What is this atomic spectra? It's light emitted from heated elements when it's passed through a prism. So when you heat up certain elements, like all of them, they'll give off light. And if you pass it through a spectra, prism, you'll see what's called the atomic spectrum. If you look right here in the upper right, here you have some sort of element and you heat it up. Here they're doing a gas, but you could also heat up a solid, and you have a slit that lets some light through, goes through a prism, and only a few bands, not like in white light, show up on the detector screen. If you notice here, let's see if I can get it larger. You notice right here for helium, it's hard to see, but there are only a few lines there. If you look for iron, notice there are a lot of lines over the atomic spectra. And these atomic spectra help play a role in helping chemists understand where are the electrons. And turns out the different line switches still off in the atomic spectra correspond to different electronic energy levels. And what are those levels? Those are association of the lines in the atomic spectra with changes in energy of electrons. So by heating it up, you've changed the energy of electrons. They give off that energy. And these energies are assigned values called principal quantum numbers. Good news, I'm not going to be teaching quantum mechanics. That was one of my challenging courses in grad school, quantum mechanics. It's a real bear of a course. A lot of very high level math. And these energies are called shell energy levels. All right, so let's bring us up to date. In the center, nucleus with protons and neutrons. All around are the electrons, and the electrons are in different energy levels. And those different energy levels we call shells. Sort of like an eggshell, but a lot more important. Not that shells aren't important, electrons are. All right, hold on. Everybody, switch is on. All right, where are the electrons in an atom, otherwise known as the electron arrangements? The electrons are in shells. An electron shell, you should know, is the region of space around the nucleus. Remember, the nucleus is the center of an atom with protons and neutrons. But the electron shell is the region of space about the nucleus that contains the electrons that have, this is important, approximately the same energy and spend their time, most of their time, approximately the same distance from the nucleus. So you have in the center the nucleus, and you have different shells. Now, they're not really round, but I'm just sort of making, I'll give you an idea, different shells with electrons. And in the electron shell, electrons have approximately the same energy and spend most of their time approximately the same distance from the nucleus. So where are the electrons? They're in the electron shell. Now, each electron shell has subshells. Remember, sub means under. So electron subshells make up the electron shells. And the electron subshells, which you should know, are the region in space within an electron shell that contain electrons that have the same energy. I don't have it down here, that are the same distance from the nucleus. So electron shells, where the electrons are around the nucleus, they're different shells, and electron shells have subshells. And the subshells have electrons that have the same energy, and the subshells make up the shells. So you have shells and subshells. Say that 5 times quickly. No, don't. When I was a student, college and grad school, and even high school, I think I started this. If something was important in the left margin of my notes, I'd put stars. And the more stars, the more important. And if it was super important, I'd put stars, and I'd also put IMP and an arrow. And guess what? 3 stars, IMP, know this. All right, the electron shells have very difficult names. The shell names are 1, 2, 3, 4. So the electron shells are shell 1, 2, 3, and 4. Now in this table, the number of subshells, which is important to know, shell 1 has 1 subshell. Ooh, this is hard. Shell 2 has 2. Shell 3 has 3. Shell 4 has 4. So the shell names are 1, 2, 3, and 4. The number of subshells in shell 1 is 1. The number of subshells in shell 2 is 2. The number of subshells in 3 is 3. And the number of subshells in 4 are 4. And as I say, shell 1 is called shell 1. The first shell, second one is 2, and so on. I don't know if I mentioned this, but now is a good time to talk about it. A couple of years ago, another instructor at COD and I were talking, and I found out how that instructor was doing his tests a little differently than I did for teaching general chemistry, like 1105, or also a little higher level, 1211. And this instructor, who's quite good, challenged me and said, when you give a test, are you supposed to be determining how good a student's memory is, or they know how to do chemistry? And he convinced me, which I'm glad he did, that my test should really figure out how well you know chemistry, not how good your memory is. Now, in the past, I would make students memorize that table I just showed you. Shell one subshell, shell two subshells, yeah, shells, shell three subshells, and shell four subshells. Then I determined, no, I don't want them to test your memory. I just want to test your knowledge of chemistry. So in the end, at the back of each test, I will have 1 or 2 pages, depending on the test. I'll do it for the final, what I call important information. And what I've done is I've cut way down on the amount of memorization you have to do in my class. Now, there's still some stuff you have to memorize, like what are the 3 subatomic particles of an atom, electron, proton, neutron, and what's the charge, electron negative charge, proton positive charge, neutron no charge. But let me open up for you in the lecture folder of Blackboard. You will see both as a PDF file and as a Word document the important information. I have them for all the tests, but let's talk about it. So everybody see on your screen now, important information, test number 1. Thank you. All right, this is what will be in the pages, the last page. I think it's just 1 page for test 1. You do not have to memorize the formulas for converting temperature scales. In the past, students had to. Now I'm giving it to you, but you have to know how to use it. And notice I will give you this table. Shell one subshell. Shell two subshell, three, four. And that's something I will be giving to you. So you don't have to memorize it, but you will know how to use it, and I'll show you how. Now, everybody see electron shells? Know this on your screen? Thank you. One of the important things about this table is shell 1 is the lowest energy of all the shells. And I see a question, comment, or something. Let me open up my chat window. Rain, thank you. And really, that's why I'm doing this. I'm trying to have you learn chemistry as opposed to test how well you can memorize formulas and stuff. There's still stuff you still have to memorize, but I've cut it way down. Now, as you go down the table, shell 4 is the highest energy of the 4 shells. And that means electrons in shell 1 have less energy than 2, then 3, then 4. Electrons in shell 4 have the highest energy. Now, it turns out Mother Nature, and by the way, I don't know if I told you this, I better. Do you know who's the greatest of all chemists? Mother Nature. She's done everything around that we see, my skin, my hair, my shirt. Notice it's Ninja Chemist Monday, not really. I have about 10 of these. I got these at Costco last year. I got a couple. I liked them so much when they went on sale this year, I bought a bunch more. But anyways, Mother Nature is the greatest of all chemists, especially organic chemists. Remember the 4 branches of chemistry? Organic, that's what I am at Sebas. Then there's physical, analytical, and inorganic. I never liked inorganic. But anyways, Mother Nature always puts the electrons in the shells, the lowest energy first before you fill up the rest. What does that mean? Well, we're going to find out this morning. or you are, I already know. So shell 1, 2, 3, and 4. The lowest energy is shell 1. The next one is 2, 3, and the highest energy is 4. And you should know shell 1 has 1 subshell, 2, 2, 3, 3, 4, 4. I will give you this table when you take test number 1 and also when you take the final. Now, let's talk about the subshells. The subshells don't have names, they have letters or numbers, S, P, D, and F. And S is the lowest and F is the highest energy subshell. Another way of putting it is everybody know this sign means in math, and we use it in chemistry, less than. I promised I wouldn't do it, and I broke my promise. So this symbol means S has less energy than P, which has less energy than D, which has less energy than F. And S is the lowest energy. Electrons, and F is the highest of the subshells. I can spell it right. And it goes from lowest to highest. This you will need to know. Now, a while back, one of the students asked me, where did I get these letters S, P, D, and F? Well, these came from the atomic spectra, the lines you saw when you heat an element and put it through a prism, the light that comes from when you heat it. And I don't know where they came up with these, but S stands for sharp, and this I'll never ask on a test what the letters stand for. P is principal, D is diffuse, F is fundamental. How they came up with that, I don't know. It's not an area of chemistry I work in, so I just accept S, P, D, and F. So subshells are in the shells. I see a question. One of your colleagues just asked how many points on a test. Test number 1, 2, 3, and 4 will be 100 points. And I better mention my test. Time out for a public service announcement from Dr. White. My test, first of all, in case you forgot, Dr. White teaches by Dr. White's golden rule of teaching. What's that? That is, I don't do unto my students what I didn't like done to me when I was a student. Yeah, I was a student a long time ago in a galaxy far, far away. For those who know Star Wars, know where I stole that. But anyways, I hated certain things when I was a student that teachers did to students. One of the things I hated, even though I was probably in chemistry, math, and other sciences, and math the best, spelling, in grade school, I was the first one down a spelling bee. I hated for my other classmates, even I didn't find it comfortable, when a teacher wrote a test that only the top person could barely finish and nobody else had enough time. That's not how my tests are. If you've done the practice problems, hint, big hint, do the practice problems, so I'll help you. My tests are designed, if we were face to face, and I've taught Chem 1105. If you look earlier on my 1105 YouTubes, you can see me in face to face when I recorded it, bring a camcorder into my lectures. There, because we were in a classroom, there would be another class coming in on certain that class. My test, I only gave the students 50 minutes to take it. And they're going to use the same type of test where if you were face to face, you should take about 50, you would get 50 minutes. I'll give you an hour. But anyways, most students are done in 35, 40 minutes, unless you haven't studied. Then you can have all day and it still won't help. So number one, my tests are designed that if you've done the practice problems and studied, you should have plenty of time to finish. Number two, my test, every question on my test, everyone, the concept behind that question I've talked about in our lecture at least twice, usually a lot more, sometimes a lot more. Like, what are the three subatomic particles? Electron, proton, neutron. What charge does the electron have? Negative. What charge does the proton have? Positive. And what charge does the neutron have? No charge. So anyways, my tests are that. And then for Chem 1105, I don't like multiple choice, but once in a while they're good. My tests are mainly short answer. Relax, they're not that hard. Students do good in my classes, like 1105. In fact, the last time I taught it about a year and a half ago, uh, I think 70, 80%, 70, I'm guessing now, but 70% listen carefully, earned A's. That's because they did the practice problems. Unfortunately, I did have one person get a D and one person get an F. That doesn't make me happy because I like to see this. Now, one of your colleagues just asked, where are the practice problems? That's a good question. Well, let me finish up. My tests usually have maximum 10 points out of 100 multiple choice. And a few things multiple choice are good, but I never give a test that's all multiple choice. Never, never, never. Now, one of your colleagues asked where to practice problems, and that's a good question. Logging into Blackboard, opening up the course. Does everybody see Blackboard on your screen? Thumbs up, people. No, maybe not. Ah. All right, thank you. Now, if you notice on the left, there's the Chem 1105 Zoom meeting login information, my syllabus, assignments, announcements, and course information. If we click on course information, you see 3 folders. I have lectures, recommended problem sets, and the answers to the recommended problem sets. And if we click on recommended problem sets, you'll see for chapter 1, let me get to, I'll get to your periodic question in a second. And practice problems for chapter 1, chapter appendix A2 and A4. These two I'll go through. Notice I have a chapter 2, chapter 3, and so on for the whole semester, including when we do organic chemistry near the end. I even have practice problems for the final. So, boy, I give you a lot of good stuff here. And there are also the answers. Now, one of your colleagues just asked, where do you find a green periodic table? And I'm going to put it in the syllabus area. In fact, I'll do it right now. Everybody close your eyes. No. Hang in there while I do this. Right now it should be red. All right, everybody see in Blackboard, in the syllabus area where it has periodic table? That's where you can find it now. So you all have access. And I'll also, either today or tomorrow, I'll send out an email with this file to you so you can also have it there and you can download that. And that's why I say there's no such thing as a dumb question. Or now, somebody asked how many questions are in a test. It depends on the test. And sometimes I'll have a question that has multiple parts, part A, B, C, and D, but the number of questions and the number of parts are always designed so you have enough time to finish. Any more questions on tests? Now, about 4 days or so before each test, I will post an announcement that you will get copied via email. You should be checking your student email frequently. And that is, I will put in that announcement and your email what, like test number 1, what chapters or appendices will be covered, how many questions will be on that test, and how many points is it. And that way you'll know, and also the date. The test will be, you'll download, and I'm thinking of changing something, so I'm not going to explain how. Now, quick question before we take a break. Oh, we got a minute. Can you all send me an email, or better yet, let me try something right now. All right, I'm taking too much time. I'll do this during the break or something. Not today, maybe tomorrow. I'll do this. Sorry about it. But I'm thinking of it. I'm going to ask tomorrow, I'll take a poll. How many of you have webcams that work? Because I think I'm going to have it like I know other instructors do during the test. I'll ask you to have the webcam on, but I will not post that video of while you're taking the test. And if I look at the clock, it's time to take a break. I'm going to take a 5-minute stretch break. I'll see you in 5 minutes. I'll be back. Time to start again. Get nice and comfy in my chair here. By the way, if you ever need really high-end office furniture chairs, there's this place in Oak Park, but they deliver, called Rework Furniture. I got a really nice chair at half price because it was used, but in perfect new condition. This thing weighs about 150 pounds. It's an awesome chair. All right, let's get back to work. We're talking about where are the electrons. Remember, nucleus, protons, and neutrons. Around the nucleus are the electrons. By the way, that's called the electron cloud because their electrons are far apart. Like a cloud is pretty, everything is molecules in a cloud is far apart. And in fact, I should mention, this won't be on a test. If we had a nucleus the size of a grapefruit or a softball, for those who play softball, this would be the nucleus. And a typical atom, the electron cloud, would go 1.5 miles that way and 1.5 miles that way, a diameter of 3 miles. I mean, it's huge and very spread out. That's why it's called the cloud. Now, electrons are in shells, and the shells have electrons with approximately the same amount of energy. And in each shell, you have subshells where electrons have the exact same amount of energy. Let's go back and talk about the subshells. Now, the subshells were given letter designation S, P, D, and F. And you should see, everybody see on their screen right now, number of electrons in each subshell. Thank you, thumbs up, people. And in shell S has, hold on, time for Dr. White to be subtle. And I should have put this. I see a question or comment. Hold on 1 second. All right, now, here we have this, oh, excuse me. Here we have the number of electrons in each subshell. Subshell S has maximum of 2 electrons. These are the max number. And usually you'll see a number of electrons. Subshell P, you can only put maximum of 6. D, 10, F, 14. Now, like the shell table, this is the lowest energy, S. As you go down, F is the highest energy. So shell S, subshell S, has 2 electrons. P, you can do maximum 6. D, 10. F, 14. Now, in the past, students would have to memorize this table too. Guess what? Let's look at important information, test number 1. And everybody see important information, test number 1 on your screen? Thank you. And in all, look, number of electrons in each subshell, S2, P6, D14, F14. You have to know S is the lowest energy subshell, F is the highest energy subshell. So again, you should know how to use this. S has 2 electrons max, P6, D, F, F14. I should have made these all lowercase, but I didn't. Now, I'm going to turn off the switch. Will this be on a test? We can also talk about what's called orbitals. Even though the electrons are in the cloud, the orbital is a region of an atom where the electron has the highest probability, whereas the highest probability of finding electrons. So a region around an atom where you're going to find most likely the electron. Now, what does this mean? If I were all powerful, and I'm not, but if I were, I could stop all motion, with a click switch, which I can't. But if I could, the electrons are moving around in certain ways around the nucleus. And if you stop them from moving, boy, would I be powerful. The orbital for each electron is the area where you would be finding that electron if you could stop all motion like that. You can't, but chemists have found a way to predict that area. And those areas play a profound effect in our life. I'll teach you more about it when we get into organic chemistry. The orbitals affect why. How many of you have heard of trans fats are bad for you and cis fats are better for you? And that's in part because of the orbitals where certain electrons are in fats and oil. Yep, that's important. I'll teach you about that later in the semester, not now. So we have orbitals and switches off. Orbitals have different shapes for the different subshells. S orbital is circular. P orbital looks like an hourglass. And there are others. Now, where are the electrons? And we talk about specification of electron structures. Electron subshells are filled in order of increasing energy. Mother Nature always fills the electrons in the lowest subshell of the lowest shell. And I'll explain what this means when we get to the big part of this morning. And electrons occupy orbitals of subshells such that each orbital acquires one before another acquires a second. This is also known as the bus seat rule. Switches off, bus seat rule. Well, electrons are like you and me. If you get on a bus and you know nobody in there, where's the first place you're going to sit? In an empty seat. At least that's what I do. Most people do. And then if all the seats are full, then you find, well, I've got to pair up with something. When it comes to orbitals in the subshells, which I'm not going to cover in this class, in 1211, I think I did. But anyways, that's how the electrons fill. And no more than 2 electrons in an orbital. Again, switch is totally off for this slide. Now, the question is, where are the electrons? And chemists have come up with a way of showing where the electrons are. One way is called the electron configuration. And the electron configuration I'm going to be subtle again. It's Monday, subtle Monday. The electron configuration is a statement of how many electrons an atom has in each of its subshells. Now, a subshell is defined by a letter and a number, and I'll explain why. And how do you remember electron configuration? Hint, numbers and letters. See board for examples. Well, I better get to work. All right, everybody see on the whiteboard, draw 3 points each, draw the electron configuration for a hydrogen. Now the question is, how do you know what to do? Well, the first thing you have to do is find out how many electrons does hydrogen have. How do you do that? You go to the periodic table. And if we go to the periodic table, how many electrons does hydrogen have? Well, first of all, you have to know hydrogen is H. The number of electrons and protons, or here we're only dealing with electrons, is the atomic number, 1. So hydrogen has 1 electron that we have to deal with. And so we have 1 electron, and the first shell is 1. And the first subshell is S, actually 1s. Actually, eh, did it again. Let's see if I can get it right. Even though I said the subshells are called S, P, D, and F, the actual subshell name and the subshell name is a number and a letter. A subshell is always called by a number and a letter. So the first subshell in hydrogen, and now let me, since I can't jump back and forth easily in Zoom, if we were face to face, I would be writing this on a whiteboard. Let's do this. Hang in there. This is electrons. I ran out of room. Now, these two tables will be given to you, but you need to know this is the lowest energy, the first century. And when you go down in both tables, this is the highest energy. Sorry about this being so busy or crowded. And the lowest energy for first electron is shell 1, and shell 1, the lowest subshell, is 1s, a 1 and s. How many electrons can you put in 1s? Maximum 2, but we only have 1. We show that by this. So 1s1 would be your answer. Again, you find the number of electrons, that's from the atomic number. You use these two tables, always fill the lowest energy shell and the lowest energy subshell. Now, let's look at, my favorite, carbon. And the same question, draw the electron configuration for carbon. What do we need to find first? The number of electrons. Let's go to our periodic table. Carbon is right here. Carbon has 6 electrons. Now, we have 6 electrons to fill. What's the first shell? 1. What's the first subshell in 1? 1s. I see a question. Nope. Not 60. You start from the lowest energy. This is the lowest energy. Always at the top, and going down, you get higher energy. You always start at the lowest energy shell and subshell. And this is why I'm teaching you this, so you know how to do it. Now, what's the maximum number of electrons we can put in 1s? Well, any s orbit subshell is 2. So I'm going to put 2 in there. Now, if we come back to here, how many subshells does 1 have? 1. We filled it up because there's only 2 electrons we can put in 1s, and there are no more subshells. Now, what's the next subshell we go to? 2. And what's the first subshell in shell 2? It's always going to be the lowest energy, 2s. Remember, subshell, name, number, letter. How many electrons can we put in 2s? And the answer is 2, NES orbital 2. So I have 2 plus 2, 4 electrons, but I need to put in 6. How many electrons can you put into any s orbital? And the answer is 2. So in 2s, I've filled it up. It's full. How many subshells in shell 2? And the answer is 2. And you always start from the lowest energy. So the first one is 2s, and then you go down this table, 2p. 2p is the next lowest energy in shell 2. Now, how many electrons can you put into 2p? Well, any p orbital, you can put 6, but I've already got 6 minus 4, because this is 2 plus 2 is 4, means I only have 2 more electrons to go. How many electrons can you put in max in any p orbital? 6, but I only have 2. So I'm done. And the answer for the electron configuration is this: 1s2, 2p2, or 2s2, 2p2. Total of 6 electrons. Let me go through it again, how I did this. At first glance, you say, oh, this is hard. It is, but with a little time and practice, it's not that hard. The first time I looked at it, I was going, what's going on here? I was lost, but I found my way. And first of all, before we go any further, let me remind you, on test number 1, important information, I will give you the table with the electron shells and the number of subshells and the number of electrons in each subshell. And I also, don't tell anybody I'm being nice over my image around here, I give you electron configuration statement of how many electrons an atom has in each of its subshells, hint, numbers and letters only. So let's go through again. Question is, draw the electron configuration for carbon. So how do we do that? Well, first of all, you have to figure out how many electrons carbon has. And we do that by going to the periodic table. Carbon, the symbol is C, atomic symbol C, and the atomic number tells you the number of protons and electrons, 6. Jada, I'd have to look up when's the first test. I don't have it in front of me, but it's in the syllabus. I just don't have a syllabus open. And somebody just helped me out and said yes. We got plenty of time before the test, not that much, but hopefully you've been doing the practice problems. Also, I better tell you, one of the things about my test is that I hated when I was a student, a day or two before the test, the teacher's still going over new material that will be on that test. How are you going to learn that? More importantly, how are you going to practice it so you do good on the test? It's hard, and that's not fair. Remember, Dr. White teaches by my golden rule of teaching, which is don't do to my students what I didn't love like done to me. And guess what? The way I have this course designed, whether it's face-to-face or like we're doing now on Zoom in the summer, I will end new material a couple days before the test, so you'll have plenty of time to practice it. And that is just how I do it. All right, let's go back and look at, for carbon, we figured out it has 6 electrons. And the first subshell you put electrons in is, you go to shell 1, and the lowest energy subshell is S, and therefore it's 1s. How many electrons maximum can we put in any s orbital? And the answer is 2. So I have 1s and it's filled. Now I have how many subshells in shell 1? 1. That's 1s. I filled it. So now I have to go to next lowest energy shell 2, And the first lowest energy subshell in 2 is 2s. Remember, you start from the lowest and go highest, and that's 2s. How many electrons can I put in any orbital, s orbital, not orbital, subshell? And that is 2. So in 2s, I put in 2. Well, we've got 6, so we got 2 more to go. How many subshells does shell 2 have? 2. The first one is 2p. The second one is 2s. Second one is 2p. Remember, subshell, number, letter. How many electrons can we put in any p orbital like 2p? And the answer is 6. But guess what? I only need 2 more because 2 plus 2 is 4. I need a total of 6. And that gives me 2 more. And that's how we do it. And let me have you try one. Now, before we do this, you had a dresser. Oh, by the way, Dr. White will never go to art school. And this is your dresser in your bedroom or wherever you keep a dresser. I spelled dresser right. And it has 4 drawers. 1, 2, 3, 4. And being lazy, I'm going to fill the first one if I have stuff in there first. And the first one has this one area. The second one has 2 areas, and so on. The third one has 3 areas in each one of those drawers. So what do? You fill this top one first, and you only got 2 electrons you can put in there. You go to this one, you fill this one first 2, and this one 6. And that's how you fill electrons using electron configuration in the subshells. Now, nitrogen. First thing you have to do the electron configuration is figure out how many electrons. Why don't you look at the periodic table? I'll give you 6.5 seconds. Go. All right, time's up. Nitrogen, chemical symbol M, N has 7 electrons. So here you have 7 electrons. Now I'll scroll up so you can see this table. And better yet, all right, I'm going to do this. And why don't you, with these 2 tables, draw the electron configuration for nitrogen, which has 7 electrons. Somebody's already on top of things. Wow, we've got some sharp students. For those of you who haven't finished, take your time. I try and give everybody time to do this work. Again, 3 points each. Draw the electron configuration for nitrogen. And I'll do it. I see a number of you are putting in the chat, which is thank you, your answers, and I'll do it. One of these days, I'm going to bring a recording of game show music to play while you're doing that. You know, like where they ask the question Jeopardy and they play that music. No, I'm not going to hum it for you. Give you a little more time to finish. All right, I think everybody's done, so I better get to work. Now let's look at how do you do the electron configuration for nitrogen. Now nitrogen has 7 electrons. What's the first shell? Well, if we look up at this busy table up here, it's 1. And what's the first subshell in shell 1? Lowest energy, and that's 1s. Oh, I got hiccups. I don't know how I got that. And what's the maximum number of electrons we can put in 1s? 2. Now, how many subshells does shell 1 have? Hope you're not getting dizzy me going up and down. 1. Well, we filled it. Now we have to go to the next shell, and that's 2. And what's the first subshell in 2? Remember, subshell, number and letter, that's 2s. So I'll do that. And how many subshells can we put, how many electrons can we put in 2s? Well, if you look at table 2, which you'll be given, 2. So I'm going to put that in there. Well, we need 7 electrons. 2 plus 2 is 4. I've got 3 more to go. So I'm not done. How many subshells does shell 2 have? And the answer is 2. And the first subshell is 2s. What's the second one? Remember, you go from lowest to next highest energy, 2s and 2p. Now, how many electrons can I put in any p orbital? 6, but I have 3 left to go. So guess what? I'm going to put it in mine. Am I done? Let's find out. 2 plus 2 plus 3, that equals 7. I'm done. And that's the electron configuration for nitrogen. Now, it turns out, as you probably learned from now, life is not always smooth and straightforward, and chemistry, there's no exception. And it turns out, as you go to the higher atomic number elements, some of the rules break down, where you fill this orbital before this subshell and shell before this one, and it gets pretty messy. Now, you could spend the next week or 2 learning all those rules in a normal semester, and guess what? You still get a lot of them wrong. It turns out there's something more important than electron configuration. So instead of you spending all this extra time learning all the exceptions to the rules, it's time for a special gift from Dr. White. Yep, the special gift. Don't go to the bank yet, but here's my special gift. If we look at the periodic table, I will only ask you to learn how to do the electron configuration up to calcium, which is atomic number 20. And for calcium, from hydrogen to calcium, 1 to 20, the rules work. They don't break down. You fill shell 1 first in the subshells, 1s, then 2 shell, which is 2s, 2p, then 3, which is 3s, 3p. Now, we don't have to go with calcium to D. Can you keep a secret? For my class, you only have to know subshells S and P. Shh. We'll learn something more important. So that's my very special gift to you, that you don't have to learn all those exceptions. Let me just quickly show you what I mean by exceptions. Now, if you look in the periodic table, this one, you can see if I do iodine, or let's even go to xenon, you start filling things differently. The 5s is then 5p, and it gets confusing. Notice for, let's do, you fill up the 4s before the 3d is totally filled up. This is called orbital diagram, but it still tells you over here, if you look over here, where the different electrons are. And it gets real confusing. My gift to you is you only have to know up to calcium, and all the rules work. And you only have to know for calcium, up to calcium, S and P, subshells. And that's my gift to you. Now, if I look at the clock, because the last break, instead of getting done at us taking our break at 10:45, I was having a good time. I went to 10:50. I'm going to end right now. We're done for today. And with that, let me remind you, tomorrow will be our lab. You should already have logged on, or hopefully in the next sometime before Thursday, you've purchased the access code for Beyond Lab Z. Hopefully you've installed it. And if you need to ask any questions, I'll stick around for a couple minutes after class. But anyways, you should do that. Tomorrow, I will teach you how to use a scientific calculator, and we'll go through the practice problems of Chapter 1 and Appendix A2 and A4, and I will show you how to use Beyond Lab Z for the density lab. And with that, I get to say, Gang Gesund, goodbye. Remember, Gang Gesund is Yiddish for be healthy. And don't forget, with the Delta variation, if you haven't gotten your vaccine, Dr. White's gotten both his a long time ago, get it. It will protect you. They're already predicting in some of the states like Mississippi and Alabama, where a lot of people haven't gotten it because they're, whatever reason, this new variation might do some serious harm this summer or fall, meaning people will die unnecessarily. Get vaccinated. And with that, again, Gang Gesund. Goodbye. I'll see you tomorrow. Don't forget, I will have my office hour tonight, 6 to 7:15. Any questions? Come on by. Bye now.